Yes, class, am I audible to all of you? Tahir, Rabah, Tariq, am I audible?
Yes,
Okay. Yes, so one portion was left from your chapter 4, that was conversion of galvanometer into ammeter and voltmeter. So sometimes in some books you will find this portion is covered in your current electricity also, in some reference books. But mostly it is in your fourth. In NCERT, it is a part of your fourth chapter also. So we are doing it here so that whatever portions of magnetic field are there, that we get to know. Okay, so yes, moving coil galvanometer. What is a moving coil galvanometer? Galvanometer is basically a device that is used to detect current. Detect current means it won't tell you how much current is flowing in your system, whether it's 5 amperes, 4 amperes, it won't tell you. But whether current is existing in your system or not, that will be dealt by a galvanometer. For example, I have constructed a proper circuit. Circuit has been constructed, wires have been made, key has been tapped up, switch is on, and everything is set up. And I have connected a galvanometer also along with the rest of the wires. Now, when the circuit is on, the current will flow through the galvanometer. When the current will be flowing through the galvanometer, as soon as the current will come, some things will happen, torque and all will act, that I'll tell you in the principle. And I'll show you the structure also, how it works. So that there will be a deflection in the coil, just a deflection in the pointer. So if there is a deflection, even a slight deflection or a huge deflection will tell you that yes, in your circuit, in your system, current is existing. Now, how much strong is the current? How much weak is the current? What is the magnitude of the current? For that, we have a device which is known as ammeter. So for that, you have ammeter. For measuring voltage, you have voltmeter. But just for detection of current, whether there is current present in your system or not, that is what we call as galvanometer. So it's just a device used to detect current. Now, whatever be the magnitude of it, that is given by ammeter. Now talking about the principle of it. See, it says that what is written? If a current carrying coil is placed in magnetic field, then it experiences a current dependent torque that tends to rotate it and produce angular deflection. Let's see this later. First understand the structure, then you'll be able to figure the principle out. Now, how is the galvanometer? All of you have seen galvanometers, I hope, in your schools, practicals. Galvanometers you have seen. Galvanometers, ammeters, voltmeters in your physics practical. Yes or no?
yes.
You people have seen. Okay. See, it's like a device appears. It has positions for tapping and tiring of the wires, red wires and black wires for the positive terminal and negative terminal of the battery. One wire is tapped like this, then another wire like this. And what do you see here? You see certain markings are made like this. You see, and then you see a pointer, a deflector is there. This keeps on moving. This is what you see. We are able to see, right, from outside. But this is not the internal structure actually which is present. When you look at the internal structure of it, you will find that this is the scale. This is the scale. This is a pointer. Now, two permanent magnets are taken and they are carved in the form of radius. So concave turnings are made inwards. Yes, I'm repeating. This is just I'm just okay. From here you will be able to understand. We are just talking about galvanometer. So galvanometer is a device that is used to detect current. Now, regarding the construction, this I'm telling right now, so that you can listen it from here. See, outside there is a scale which is visible to all of you. When we go into the deep structure, which is inside the galvanometer, if you open the galvanometer, what do you see inside? You see two permanent magnets, one is north polarity, other one is of south polarity. Magnets are taken and they are carved concavely. So concavities are made. So these are what? These are the permanent bar magnets. They are the permanent bar magnets. Now, why are they carved in the form of concavities? This reason is that we have in the center a soft iron core. This is a soft iron core. Now, on this, now can you see these lines? These are basically wrappings of wire, like copper wires or any conducting wires. These are just wrapping on it. Suppose this is the center soft core. So on this, like this, wire wrappings are made like this. The soft center core on which the wire turnings are made like this, like this. This is the soft center core and this is the wire turnings. Now, in the center of this core, when the wire is not in the center exactly of this core, a spring is connected. This is actually a spring. This is a spring. A spring is connected. And on this spring, at the center, you have the spring, and on this spring, the pointer is connected. Fine. Now, this is a wire. So when current flows, when you connect it with your circuit because of presence of circuit, because of presence of batteries will discharge the current and current will flow in your circuit. Current will flow through these wire turnings that is wrapped, right? Current will flow through these wires. Now see, as soon as the current will be flowing through these wires, what will happen? This is like a current carrying conductor now. It's a current carrying conductor, right? So current carrying conductor produces magnetic field. That is what we have been studying throughout. Now these magnetic fields, when they come out of it, because of the concave endings of the bar magnet, they come out to be radial. They are present all along the radius of the curve like this. So what are these? These are the radial magnetic fields. Radial magnetic field, and this is uniform. Now, as soon as the magnetic field comes, we have studied in the last class. I have made you, that's why I do torque before. Torque is actually part of your 5th lesson. I have told you this. So now when magnetic field comes into action, we know torque is equal to M cross B. So there is a torque in your system, which torque does what? Torque is a rotational force. So it rotates object. So what happens? As soon as the torque comes, it rotates it. When it rotates it, you are able to see the tip of the pointer, which is giving you a mark on the scale like this. A detection is made. This is how a galvanometer works inside. And on outside, you are able to see just a scale, and you are able to see the deflection of the pointer. All right, that is just the. It's just that the pointer is just helping to give the it is telling you yes or no. Yes, a current is present in your system, or no, current is not present in your system. Now, if it's a very large deflection, it means a very strong magnitude of current is there. If it's a very slight deflection, it means a very small amount of current is there in your system. So even if the slightest amount of current is there in your system, it will detect current. So, but regarding the magnitude, how much current is being processed, that is given by the ammeter. All right, so this is how it works. Now see, now come back to its principle. What is the principle? It is saying if a current carrying coil means the wire turnings. Current carrying coil is placed in magnetic field. Constant means magnetic field has to be uniform. Magnetic field is constant. Then it experiences current dependent torque. And what will torque do? Torque tends to rotate it, so angular deflection is produced. If in the soft iron core, you are placing a pointer and this is getting deflected due to torque, rotational effect is occurring. So that is producing angular deflection, means some angle is swept. So if a current carrying coil is placed in magnetic field, then it experiences a current dependent torque that tends to rotate it and produce angular deflection. Let us find out how much displacement occurs. If a pointer is rotating, some angular displacement is occurring. Initial position was this. Now it has moved here. So certain angular position, angular displacement is being moved. So how will you find out the angular displacement? See, there are two torques in your system. One is the deflecting torque. Deflecting torque tends to move it, produces deflection, which we have studied in the last class. It was N number of turns, area, current into magnetic field, NAIP, this we have studied. Now, if you remember in your 11th class, last portions of waves and oscillation, you must have seen spring mass system. So many systems are there in your syllabus. So force is actually restoring force, the force that brings the object back to its mean position. Suppose if I stretch a spring, so spring's mean position is this. Now I'm stretching it beyond, so it will come back to its mean position. If this is the spring, let's say I'm holding the spring. When I'm pulling it, I am exceeding its mean position, and then the spring is coming back to its mean position. So why is it coming back? If I have pulled it, which force is making it move back to its mean position? That is the restoring force, which is equal to F is equal to minus K.
Minus K.
Yes, very good. So this is your translation one. If you have rotation, the same thing in rotation, translate everything. This becomes torques minus K, and linear displacement becomes angular displacement. So what is deflecting torque is this, and your restoring torque here, this will be K theta. So you can equate both of these. So NAIB is equal to K theta. From here, we wanted to find out the value of theta. So theta is NAIB divided by K. Theta is actually the angular deflection. Angular deflection. K, see, K is a spring factor. If we talk about K, K is a spring factor. For different systems, you have different values of K. For example, if we talk about a pendulum, so the value of K becomes 2 pi, right? Under root L by G is already present, so you get 2 pi, the value for the value of time period. So different values of K are present depending upon whichever system you are, it is consisting of. Like if we talk about, take any system, actually K is not fixed. K for any system can be any value, it can be any value, but do not remember it as a spring constant. Spring constant is different. See, spring constant is just valid for a spring mass system. Suppose if I give you this, a spring is there, a block of mass M is there, K is there, so F is equal to Kx. This value of K is the spring factor. If I give you pendulum, pendulum is moving to its extreme position and then back to its mean position. Then coming back, then again to extreme position, coming back to its mean position. Then again, value of K is different. That's why we call it as a spring factor. Means it is not just valid for spring. Spring constant is different, spring factor is different. Right now, we call this as torsion constant. When this K comes in the context of moving coil galvanometer, then this K becomes torsion constant. So this is just a constant value for different systems. We have different values of it, and hence we have the different name. But in general, if you want to talk about it in layman terms, when you are not aware of the system, then what you will do? You will use the term spring factor. So spring factor is a broader name. It's a big heading, spring factor. Under it, you have different types of spring factors, which even have their further names. Like for spring mass system, we use the term spring constant. For moving coil galvanometer, we use the term torsion constant. Like this, we have different values of K. So in general, the actual heading is spring factor. But here we are talking about it, so it will become spring torsion constant. Note it down here, current sensitivity, we will do it afterwards. Note it down from here. Conversion of, heading is conversion of galvanometer into ammeter and voltmeter. But before that, we have to have the basic idea of moving coil galvanometer. Note down all these, and principle is very important class. Principle is asked in the exams also. You have to write the principle as it is. Exact statement. So rote learn it, remember it the whichever way you can. But principle is extremely important. Angular deflection means the angle that has been swept by the pointer. Theta. When the pointer will move, some angle will be formed here. That is what is angular deflection. Angular displacement, you can say, same thing.
I'm gonna scroll up. Hello.
Yes, class, talking about the sensitivity of a galvanometer. So sensitivity of a galvanometer means what is the function of galvanometer? Whenever there is a current in your circuit, it will detect. So sensitivity means that if a very, very small amount of current is there, all right. So what should happen if a small amount of current is there? For a very small amount of current, this should be the deflection. This was the initial, this should be the deflection, that is. But suppose for, let's say, 0.3 amperes, I am getting this much deflection. Very slight deflection I am getting. And 1 galvanometer I am having for the same amount of current, that is 0.3 amperes. This much amount of deflection has been shown. So I'll call this galvanometer, second one, as a sensitive galvanometer, because for a very small amount of current, it is giving me a large value of deflection, right? It's, you can relate it with the word sensitive word. The way in common English literature we use the word sensitive word. You can use for people also. We use, say, no, some person or this person, that person is very sensitive. So that means what? For small thing that is occurring, which is not a very big issue, the person reacts more. So we say the person is feeling more. So we say the person is sensitive. Same thing is here also. For a very small amount of current, the amount of deflection is more. So you will say the particular galvanometer is sensitive, or that the amount of deflection depending upon the magnitude of current which is being given. This is what is meant by sensitivity. All right, now we have sensitivity in terms of current and voltage. You have current sensitivity and you have voltage sensitivity. For both current and voltage sensitivity, this comes in your exam, and best way to remember it, learn current and voltage side by side. So you'll be able to remember it. Current is what? Current is deflection per unit current. Current sensitivity is deflection per unit current. That is deflection. We have just derived it per unit current. What was the formula of deflection? NAIB divided by the spring, that torsion constant K, and here I. So I got cancelled. Value of current sensitivity is NAB divided by K. This is the value. Next we have is voltage sensitivity. So voltage sensitivity is also same. Deflection per unit voltage. Current sensitivity is deflection per unit current. Voltage sensitivity is deflection per unit voltage. Just remember deflection per unit the quantity. So for current sensitivity, deflection per unit current. For voltage sensitivity, deflection per unit voltage. Like this one. This you can remember right now. Theta by voltage. Yes, what is voltage? Voltage is current multiplied by resistance according to your Ohm's law. So put in the value. Current is, you are having the value of current as how much? Resistance will be there in your answer. See, theta by I. Theta by I is current sensitivity, right? Theta by I is actually current sensitivity. So what is the value of current sensitivity? NAB divided by K. This is theta by I. And what about this? Resistance. This is voltage sensitivity. Do not be confused. This R is resistance. How have we applied resistance? We have applied resistance using Ohm's law, which you have studied in current electricity. All right, this is voltage per unit and current per unit, deflection per unit current, and deflection per unit voltage. Note down sensitivity also. Then we'll do first conversion of galvanometer with each device. First with ammeter, then voltmeter. Separate we will do. Class, now first let us do conversion of galvanometer into ammeter. Now what does this mean? This means that if you have a galvanometer, you are having wires, you are having key, entire circuit you have constructed, but you do not have the ammeter with you. So how will you calculate the value of current? Because I have told you galvanometer will only give you the deflection, and deflection will only prove that yes, in your system there exists a current, in your circuit there exists a current. All right. Now see, conversion of galvanometer into ammeter. So how we have to perform calculations by ourselves. We'll set up the circuit in such a manner that we are able to find out the value of current. So if I just have a galvanometer, what will I do for conversion of galvanometer into ammeter? I'll connect a resistor in parallel. This resistor is called a shunt. This is connected in parallel and this has a very small value of resistance. The value of resistance is very small. This we call as the shunt. It's just a name given to this. This is nothing new. It's normal resistor. It will follow ohms law. Its SI unit will be ohms. Series, parallel connection, everything will remain the same. It's just that a specific name is given. And there is even no record of why the name shunt is given to it. It's just that since it is crossing it is parallel to the galvanometer, that's why we are having it. G, I have taken it as the resistance of galvanometer because resistance of shunt we'll take the resistance if we are connecting another wire. So that's why to make this resistance unique, we are taking it as G. Now suppose current I is flowing. So IG current will go in the galvanometer. If IG from I current, IG has gone. So how much is left? I minus
IG, I minus I.
yes, I minus IG is left. Now this is what is happening. Galvanometer is there. You have connected a resistor. Ammeter is still not there in your system. You want an ammeter. What is the function of ammeter? You want the current, you want the resistance, right? So now this is your ammeter. Why? Why is this an ammeter? Because you know the series and parallel combinations formula, right? You are aware of the series and parallel combinations formula. So potential difference across both the ends will be the same because they are in parallel. So look here. Potential difference in this branch will be equal to potential difference in this branch. So how do we write potential difference? V is equal to IR. This is how we write potential. So current is IG, resistance is V. So potential becomes IG into G. That is the potential across the galvanometer. IG into G. Potential difference across shunt. Current is I minus IG. And what is the resistance I have taken? I have told you I have taken the shunt's resistance as S. This is taken by convention. So you also know in the formula whenever you are writing it, even if you're deriving, use G for resistance of galvanometer, use S for shunt's resistance. Because it is standardized, it is also written in your NCRT. So for the examiner also it will be easier to check. And in boards you have to apply all these tricks because a particular mark sheet is made and the examiner will just match it. It depends what kind of examiner is taking your paper, that's a different thing. But if these conventions are already mentioned in NCRT, so you should prefer these only. So yes, that becomes I minus IG into S. Now, anything whichever you need, you can find out using this formula. What will be the shunt's resistance? This is commonly asked more than current and anything else. So this is IG, that is current through the wire of the galvanometer. Current through the galvanometer, resistance of galvanometer by current through the wire, that is left. This is the formula. Note it down, then we'll see how to construct voltmeter. But just remember this point very well. And class, this becomes confusing also, whether it was small resistance or greater resistance or connection in parallel or series, because you will see just the opposite in voltmeter. Note it down, or let's do one thing. Let's complete voltmeter also now so that you can identify both the things parallel. See, for voltmeter, what do we do? The value, see, ammeter's function we are performing through calculations. But if shunt is what is doing, shunt is facilitating the function. If there is no other resistance in the circuit, With just the galvanometer's resistance, we will be able to find out nothing. So we require something else also, and we do not have a proper ammeter also. So what we do, we have connected shunt along with the galvanometer. Now, whatever of shunt resistance will come, that will be the shunt's resistance value. That won't be the entire current. This I am telling you, most commonly question asked is shunt's current. If suppose you know the shunt's resistance, you know everything, you just don't know this I, that you can find out. So using just this formula, you can find out now anything. So that's why galvanometer wasn't sufficient. We had to construct a shunt. Now with the shunt, we are able to do the work of galvanometer also and ammeter also. Now clear?
Yes.
And when we are talking about voltmeter, so what we do, just the opposite. Connect a high resistance in series. There it was parallel, here it is series connection. In ammeter, you have small resistance value. Here in voltmeter, you are having the resistance magnitude higher. This is the resistance. Now for this resistance, because this is just an external resistor, this is not crossed parallelly. So this is not shunt now. Shunt is unique in itself. That's why I'm saying use the term shunt for it. Don't use a series or a parallel resistor connected. Here use the term resistance. Then again, current through this will be IG. Okay. Now total voltage, if I ask you through the circuit. Okay, before the voltage, tell me what is the total resistance in this circuit? Total resistance in this circuit. This is the circuit
V
given.
plus IR.
G plus R, very good, Shavesh. Because they are connected in series, they are two resistors. Have you forgotten the rules of current electricity? We had no two resistors are in parallel. So your R equivalent will be G plus R, right? Now V is, and what is the current in your circuit? It is IT. So what will be potential? Potential is current multiplied by resistance. So potential is current, that is IG, and resistance is G plus R. Now, what will be the voltage? Voltage will become, okay, let's find out this R. No, let's write the value of resistance instead of voltage, because now this formula is sufficient. You can find out anything. If three variables are known, that fourth one you can find out. But as I've said, questions are more on resistance part, the way the questions were more on shunt part. So resistance will become, see, V divided by IG will be G plus R. So resistance will be V divided by IG minus C. So now you can see the difference between shunt and the resistor, and how voltage is involved and how here resistance is involved. One question we will do, and we'll complete with this lesson, and we'll start the next lesson. Next lesson is very small, and for the next lesson, you people are there on the WhatsApp group, no? I think Shavesh also has texted something on the group. Everybody is there on the group? Those who are present today? Shavesh is there. What
Yes.
about others?
Yes, ma'am.
Rava is there. Huma?
Yes.
Okay, then fine. I'll share a table for the next lesson. Okay, let me tell you that afterwards. First note it down.
Ma'am, the group which is created by Learnivio, right?
Yes, yes, yes. The group that is created by Learnivio.
You're muted.
Am I audible now? It was muted.
Yes.
Okay, okay. Ammeter of resistance 0.8 ohm can measure currents up to 1 ampere. So when ampere, yes, up to 1 ampere. So this means in our circuit, galvanometer is present, a shunt has been connected, right? So when it says ammeter of resistance, what is your ammeter? Your galvanometer has actually been converted into ammeter. So this means this is the resistance of the galvanometer because there is no ammeter in your circuit. So this is G, resistance of galvanometer. It can measure currents up to 1 ampere, mean the current that is present through the galvanometer. So Ig, which we consider in the equations, Ig is 1 ampere. And resistance through the galvanometer, it's 0.8 ohms. Now the question is saying what must be the value of shunt resistance so that the current is 5 amperes. So total current is 5 amperes. What is the value of S? So it's a formula based question. So first part, see, G is 0.8 ohms. Ig was 5 amperes, 1 ampere. And this is total is 5 ampere. And what do we need? We need the shunt in the first part. So shunt is Ig into G divided by I minus Ig. 1 into 0.8 divided by 5 minus 1. So 0.8 by 0.8 by 4. So this is 0.8 divided by 4, 0.2 ohms. What is the combined resistance of ammeter and shunt? Yes, this is important. This part is important because first part was just formula based. It says what is the combined resistance of ammeter and shunt? What is the resistance of ammeter? Resistance of ammeter is 0.8 ohms, right? Shunt's value we have calculated 0.2 ohms. So now it is saying combined resistance of ammeter and shunt. It means the resistance of galvanometer which is connected and the parallel connection of shunt. So how do we find the R equivalent? 1 by R1 plus 1 by R2. So this becomes 0.8 into 0.2 divided by 0.8 plus 0.2. 0.16 divided by 1. So that becomes 0.16. This is it. One more part could be constructed from this part, but this question is related to conversion of galvanometer into ammeter. That's why this is not involved. Because when we are talking about voltmeter, series combination will come into action. Note down the solution. Text me done.
Can you scroll up? Yes, sir.
Yes, bar magnet. Now, this is chapter number 5, that is magnetism and matter. That was moving charges and magnetism, the one which we have covered, magnetic effects of electric current. This is magnetism and matter. Now, all the lessons which are left in your first book till EMA, these are very small lessons. All right, magnetism and matter, AC, EMI, EM wave. These 4 lessons which will now come, these are very short lessons and these won't take so many classes that are taken for all these lessons which we have covered till chapter 4. Then in your second book, you have lengthy lessons, which are your ray optics and all. But right now, These are very small lessons, so try to cover it along only, because these lessons will be completed faster in comparison to the other lessons. So if you'll not revise, then it will pile up. Yes, so this is chapter 5th of NCERT. It's the first topic that we'll be dealing in here, and which is in detail, is topics and the concept of bar magnet. Now, whatever we'll study in the magnetics regarding a bar magnet, we'll compare the same with electrostatics. Like I have told you, there are certain analogs. Electric field becomes magnetic field, dipole moment becomes magnetic dipole moment, like this. So all the things we'll be comparing. So that's why it will be a revision of your electrostatics as well. So keep on revising your electrostats. We'll do it here only. It says we deal with natural magnets or permanent magnets. See, natural magnet, you have a topic which is known as earth magnetism. Earth magnetism means, it means that if earth is acting as a magnet, then this becomes a natural magnet. And then you have artificial magnets also present. They are permanent magnets, which are your bar magnets. So this bar magnet we'll deal first, then we'll deal with earth magnetism. In between, you have certain topics like ferromagnetism, diamagnetism, paramagnetism. These are substances, these are types of magnetic bar magnets which are present. So for that, you have to remember a lot of theory portion, for which I'll send you a table. In that table, everything is given. I'll share it on WhatsApp today or in the next class, because tomorrow I'll share it. Then in that table, everything will be given as it is. Questions will come from that table. But whatever things are mentioned, just write it as it is. I'll discuss it once, whatever basic things are there, I'll discuss it in the class. But that is a very theoretical part which you have to remember. You have to memorize it. So learn it. Yes, bar magnet. Bar magnets are of two types. See, it can be artificial and one more thing, they are permanent. Means they are made by man. They are not present naturally, like the crust, from the crust of earth or what. But once they are made, they are permanent. Even if you have a bar magnet, it doesn't expire, right? If you are keeping it after a long period of time, even if you're taking it, will be having magnetic properties. So it means it's artificial and it's permanent. Now, certain properties are there. First property is attractive property. It's a very basic property. Attractive property means what? North and south, they'll attract each other because they are the unlike poles, opposite poles. And the poles of same polarity, like south, south, or north, north, they will repel each other. This is valid for charges. This is valid for magnetic poles also. That is north and south pole. Then directive property means, see, suppose I have taken a bar magnet. North pole, south pole. And I've tied it with the help of a string and I've kept it freely like this. So initially, how is the position of bar magnet? When it is freely suspended, it would be like this. But what will happen? After a while, I'll notice that it will align itself in north to south direction by itself. So even if suppose this is a bar magnet, I've hung it with the help of a thread like this. As I'm moving the thread, this wire is there. All right. This is kept like this, but slowly I will see this will be arranging itself. So it has a directive property. Directive property means from this position, it will arrange itself like this. That is north to south direction. So freely suspended magnet always align in north to south direction. That is the second property. Magnetic monopoles do not exist. Means, see, if suppose I have a bar magnet, north polarity is here, south polarity is here, right? Now I have broken the bar magnet in between. One part is here, one part is here. This is having north polarity, this is having south polarity. So what should happen? If this is a magnet, then I should say this is the north magnet and this is the south magnet. But monopoles do not exist. Means a magnet solely cannot exist without its opposite pair. Means north pole has to have a south pole opposite along with it. So when we are having North Pole, so what will happen? This is a broken piece. I have broken this magnet in between. So what will happen? This portion, no, that is left, the other part from which it has been broken, this will develop south polarity automatically. And here north polarity will be developed automatically. So at the end, what you will have? You will be having just what will decrease is the length. Length will decrease because you have broken it. So length will decrease, but polarity will same because it cannot exist independently. See, we have talked about charges. Charges, you have seen electrons exist independently. Protons exist independently. You do not need a proton for the existence of electron, right? Because they are monopoles in electrostatics can exist. Monopoles, mono means one, poles means polarity. So polarity is positive, negative, north, south. So electrostatic monopoles can exist. Plus charge will exist in your system. You can even have a system where just negative charges are there or just positive charges are filled. But in magnetism, you do not have a complete north pole located magnet. It will have south polarity on the opposite side automatically. Fine. So these are the basic properties. One more, magnetic induction. See, property to induce magnetism in magnetic substance. This basically means, suppose I have an iron ball. The best example is if I take the example of iron ball. Iron ball is not magnetic. If I give you an iron ball, suppose I have given you this iron ball. Fine. Will it be magnetic in nature? If you try to stick it on a wall or on a metallic wall or somewhere, it won't stick by itself. But what is meant by magnetic induction is, this is iron ball. I have brought a bar magnet. North, south, I have brought a bar magnet. And let's say this is the bar magnet. And I have rubbed it. For a lot of time, I have rubbed this. I have rubbed this entire iron ball for a lot of time with this bar magnet. This has magnetic properties. This doesn't. So it will induce some of its magnetic properties for a short period of time, that is temporarily in this iron ball. So it wasn't initially magnetic, but after rubbing it with bar magnet, what will happen? This will acquire certain certain magnetic properties. So this property to induce magnetism in magnetic substances. Magnetic substance means if this is an iron ball, then only it will get magnetized. Certain substances are there which have the tendency to get magnetized. Some substances are there which can never be magnetized. If I take a piece of wood and I try to rub it with a bar magnet, with a horseshoe magnet, different types of magnets which are present, nothing will happen in the wooden piece. But if it's metallic, there are certain magnetic substances. Magnetic substances, it does not mean that they have the magnetic property. It means they have the tendency to gain the magnetic properties. So if iron ball is there, for iron ball, it can acquire magnetism for a short period of time. That means it can be temporary. Permanent magnets are not made like this by just rubbing. By rubbing, you just give them temporary magnetism. But this is occurring. That is magnetism. Yes, say.
Like rubbing with bar magnet.
Not rubbing with exactly bar magnet, like rubbing with any magnet. This was just an example that I'm telling you.
Okay.
There are so many types of magnets available. Horseshoe magnets are available. Even different shapes of magnets are available. Right? So any magnet.
So
Property.
this core will gain magnetic properties.
This will gain magnetic property. Yes. Depending upon the magnitude of magnetic field this is holding. If it's a very high magnetic field, if you will try to rub it, it will acquire magnetism for a short period of time. You will notice that this is also repelling. If you bring another bar magnet, or another magnet, you will see soon it is also repelling. It means it has acquired certain magnetic property. So point is that in magnetism, whenever we are talking about, right now we are focusing on bar magnet. That's why I'm constantly using the term bar magnet. But this property is valid for any metallic substance or any substance which can be rubbed through any magnet. You can take a horseshoe magnet, you can take a block of magnets also exists, that can also be present. Fine. So this tendency to acquire magnetism is also a property of the bar magnet. That's why we are studying it under this heading. Till here, is it clear to all of you? Humam,
Yes, sir.
Shahid, what about you? Shahid, clear? Rabah, Tarif, clear?
Yes, Miss Clear.
Oh, then from a fresh page, start noting it down. This because this is a new lesson, so do not start it from where you have completed the last lesson. From a fresh page, start this.
Can I scroll up? We're done.
Please text me done once you have completed till here.
Scroll up.
Shahid completed. Fine, you can leave. All those who have completed, you can leave. Time is already up. Tomorrow we'll continue this.